Welcome to today's lecture on Guidance, Navigation, and Control, or GNC, a subsystem in my Space Robotics course. By the end of this lecture, you'll be able to define the GNC system, identify typical requirements and design considerations, and understand how different technologies are applied for guidance, navigation, and control across satellites, landers, rovers, and aerial vehicles. GNC answers three questions. Where am I? Where do I need to go? And how do I get there? Guidance generates the desired trajectory. Navigation estimates the current state, and control applies the necessary forces or torques to follow that path. Let's break this down further step by step. Let's say we have some space robot in a space environment. That space robot has sensors that provide raw data. On board the robot, a determination algorithm processes these signals to estimate your position and attitude or orientation. Path planning then uses the robot's current position and attitude as a reference to generate the next desired state. Control then uses those state estimates and desired state to generate actuator commands to keep the robot on course. The space robot implements these actuator commands and moves through the space environment. This is a continuous feedback loop that keeps incrementing until mission operations cease. When we think about guidance, navigation, and control, or GNC for short, it really boils down to those three essential questions. First, where am I? That's the job of navigation, which requires the system to determine the robot's state, its position, orientation, to a certain level of accuracy, precision, and time frequency. I challenge you to think about that for your particular mission as a requirement. Second, the question of where do I go? That's the domain of guidance where the system must generate waypoints or desired trajectories at some frequency and level of detail, which I also challenge you to define for your mission. And then finally, the last set of requirements, that's where control comes in, converting those waypoints into actuation commands that are executed with the needed accuracy, precision, and time frequency. The GNC system architecture and requirements will vary significantly depending on whether we're dealing with an orbiter, a lander, a rover, or an aerial vehicle, and also the space environment that robot is in. This lecture is going to overview various GNC architectures for different space robot systems, separated by the type of environment and the robot mobility type. Each system has key challenges and unique modes that drive the GNC sensing, actuation, and algorithm design. For orbiters like the James Webb Space Telescope, GNC first needs to detumble the spacecraft after separation, and then maintain precise pointing for communications and science instruments. For thermal constraints, even influence the desired attitude. So here, the key GNC modes are attitude, determination, and control. Landers like the Mars 2020 entry, descent, and landing system face high-speed descent through a thin atmosphere. GNC must manage stability, switch between sensors and control regimes very quickly, and safely transition to terminal landing phases like powered descent or sky crane maneuvers. For rovers, GNC governs mobility, figuring out how to autonomously traverse unfamiliar terrain, avoid hazards, and execute driving commands. That includes path planning and estimating wheel slip, which is crucial when driving on sand or rock. Some unique GNC modes include path planning at different location waypoints in a trajectory, and estimating slip on wheels during traverses. And for aerial vehicles, like the Ingenuity helicopter, the challenges include low gravity, Martian dust, and gusty winds. GNC here relies heavily on visual inertial odometry to estimate motion in real time and to hover or navigate precisely, even without GPS. Regardless of what robot form or environment you're designing for, you should define what targets you want to localize and point to within some accuracy and precision. This slide shows a template, which I will provide to you, that helps you systematically break down those requirements for each subsystem and component of your space robot. Let's walk through the columns so you understand how to fill it out. Subsystem and component describe what part of the robot we're considering, like a camera in the payload subsystem or a transmitter in the communications subsystem. Target refers to what that component needs to point to or localize to. For example, the Earth or the Sun, a science target, or a ground station. Position relative to target is used for localization. It defines where some reference point on the component, like the view axis of a camera or a GPS antenna, needs to be located relative to the target. For example, a camera might need to be positioned 1 centimeter along the plus Z axis from the surface it's imaging. The next column, axis to align and frame of axis, is for pointing purposes. It tells you how the robot needs to orient itself to accomplish the function. For example, aligning the plus Z axis of the spacecraft with nadir when imaging Earth. The next column, accuracy, describes how close the robot's actual pointing or position needs to be to the true value, like within 45 degrees of the sun so that I can charge or image. Precision reflects how consistent or high resolution that pointing needs to be. A camera, for instance, might need 4 degrees of angular precision to resolve a location like Hawaii on the surface of the Earth in both latitude and longitude. And finally, the function column summarizes what kind of behavior within GNC is needed. Does the component require pointing? Does it prefer a spin stabilization, or is it solely about localization? This kind of table is critical because it lets you trace GNC design decisions back to specific subsystem needs and ensures your sensor and actuator choices directly support those functional requirements. Now we'll get into sensor and actuator design solutions with some quick context on what's available in a space environment. There are not that many references in space compared to Earth, but of the references in space, here's what's used for navigation purposes. In space, we don't have GPS satellites everywhere, so the spacecraft have to rely on natural environment references. There aren't that many consistent cues out there, but here are the most common ones we use for navigation. A planet limb, like this Earth limb right here, refers to the edge of a planet as seen from orbit. The curvature of the limb helps spacecraft orient themselves relative to the planet. Sensors like horizon detectors can identify the sharp brightness contrast to estimate orientation and altitude. Local variations in gravity, called gravity anomalies, and depicted here in this heat map, arise from uneven mass distributions below a planet's surface. These variations can slightly tug on a spacecraft and are useful in estimating position, especially in low lunar or Martian orbit. Gravity mapping missions like GRAIL have taken advantage of this. Many planets also generate magnetic fields through motion of their liquid cores. A magnetometer can measure the direction and strength of a local field. Comparing this with a planetary magnetic model, like the one seen here, allows estimation of orientation, like using a compass in space. Star trackers use the known positions of bright stars as a fixed reference, like constellations shown in that picture. Because stars are effectively motionless on mission timescales, they provide an inertial frame. Star fields are compared to onboard catalogs to calculate precise spacecraft attitude. Planetary surface features include craters, ridges, and rock formations. Onboard cameras can match observed terrain with known maps for localization. This is called terrain relative navigation, and it's how missions like Mars 2020 land so precisely. This picture shows the identification and matching of various lunar crater and surface features. And finally, the positions of various celestial bodies like the Sun, Moon, and planets, as can be seen in that diagram, can also serve as navigation references. Measuring their angles relative to each other or to the spacecraft sensors allows estimation of position and heading in space, much like how ancient sailors used sextants. Together, these references form the backbone of navigation in deep space and planetary missions. So remember this diagram of the variance of space environments out there? Depending on where we are in the solar system or in deep space, we have different natural references we can use. Let's walk through each case, starting with Earth's orbit. Earth's orbit is one of the most data-rich environments. We can use gravity, stars, visual references from the Earth's limb or surface, and Earth's magnetic fields, all of which are well mapped and reliable. Around small bodies like the asteroid Itokawa, the environment is much more limited in what you can sense. Gravity is extremely weak and irregular, so we rely heavily on star trackers for inertial orientation and surface features of that body from onboard cameras to estimate motion. essentially visual odometry. On the lunar surface, gravity is strong enough to support inertial navigation, and star trackers work well because there's no atmosphere. We can also leverage surface features for terrain relative localization. But there is no significant magnetic field, so that's not a viable reference for sensing. Moving on to Venus. Venus is tricky. The thick atmosphere obscures star visibility and distorts surface imagery. Still, we can use its gravity field, which is well characterized from orbiters, and surface features, typically mapped through radar. Magnetic field navigation is not viable here either. Mars offers a rich set of references. We can use gravity and a weak but usable magnetic field in some areas. Mars's relatively clear skies also allow star trackers, and there are plenty of surface features to support vision-based navigation. That's why terrain relative navigation worked so well on Mars 2020. And then finally, Titan's hazy atmosphere makes star sensing difficult and obscures direct views of the surface. However, you can still use gravity and radar-based mapping for surface features. The magnetic field is very weak and unreliable here, so that gets more of a question mark. In that table, we'll show the questionables with a tilde. Now let's look at what physical phenomena we can leverage to move or stabilize a robot in these different environments. Whether it's gravity, fluid flows like air or liquid, each environment gives us a different set of tools. In Earth's orbit, we can take advantage of gravity to maintain an orbital path, magnetic fields for torque via magnetorquers, and fluid dynamics for drag-based control or aerobraking in low Earth orbit. Itokawa's gravity is extremely weak, so traditional gravity-aided trajectories don't work so well here. There's no atmosphere for fluid-based actuation and no magnetic field. However, the granular surface allows us to leverage terramechanics, like bouncing or hopping locomotion using contact forces. The Moon has usable gravity and well-characterized terrain mechanics. There's no fluid flow to generate lift or drag, and no global magnetic field to torque on. So landers and rovers rely heavily on gravity-aided descent and wheel-soil interaction models. On Venus, we get everything but a magnetic field to leverage. Venus has a thick atmosphere, so fluid flow is very relevant. Think parachutes, or aerobraking, or even sustained flight through a balloon. Its gravity is similar to Earth's, and terramechanics matter once you're on the surface. The magnetic field is negligible though. Like Earth, Mars gives us gravity, fluid flow, and terramechanics. Its thin atmosphere still allows for lift and drag. Ingenuity proves this. Magnetic field cues exist, but they're patchy, so not reliable for consistent control across the globe. And then finally, Titan's thick nitrogen atmosphere and low gravity are perfect for fluid flow-based motion. Great for parachutes, balloons, or aerial flight like the upcoming Dragonfly. The surface is soft and varied, so terramechanics is important for landers and rovers. The magnetic field is uncertain and likely weak, so we mark it here as a maybe. Each of these environments demands a different set of sensing and actuation strategies. Understanding what physics you can rely on is key to designing a motion control system that works. We're now going to review various hardware options in sensing and actuation for the various types of space robots in their specific space environments. When designing an orbiter, we want to sense our orientation and motion using reliable environmental cues, like stars, the sun, Earth's limb, gravity gradients, and magnetic fields. This slide shows how we actually measure those physical references using specific sensors. Let's start with the one sensor you'll always have, the Inertial Measurement Unit, or IMU. Every spacecraft, regardless of its orbit or destination, can measure its own acceleration and angular rate, which is what an IMU provides. IMUs provide high-frequency updates, but they drift over time. So looking at this column, you can see these numbers. The accuracy ranges from about 0.0003 to 1 degree per hour, as shown in the table here, so they need to be periodically corrected using external references. One of the most precise references in space is a star field. Star trackers, like the one shown in the top right image, observe star patterns to an onboard catalog. With multiple stars in view, they can return full 3-axis attitude to within arc seconds, which is equivalent to 0.0003 to 0.001 degrees. They're great for inertial reference frames, but do require clear sky views. Another absolute reference is the sun. Sun sensors, as shown in the middle diagram, detects the sun's location relative to the spacecraft body. They're simpler and lower cost than star trackers, but less precise. Typically, accuracy is around 0.01 to 3 degrees, and they fail in eclipse situations. We can also use the Earth's limb with a horizon sensor, like the one shown in the Earth diagram on the left. This is useful for low Earth and geosynchronous orbits. These sensors give about 0.1 to 1 degree of accuracy, depending on the orbit. But they only work when Earth is in the field of view. We also discussed magnetic fields in the environmental references. A magnetometer is commonly integrated into an IMU. A magnetometer can measure the direction and strength of the local magnetic fields. These are especially useful in low Earth orbit and provide attitude references when compared with Earth's magnetic models. If you look at the very bottom row of the table, you can see that their accuracy drops off at higher altitudes and inclinations, typically 0.5 to 3 degrees below 6,000 kilometers. Overall, your orbiter sensing strategy is about layering and using multiple of these sensors. Use the IMU for high-rate motion tracking, then periodically correct using these environmental references, like stars, the sun, Earth's limb, or magnetic field, depending on what's available in your orbit. Each sensor gives you different degrees of freedom and accuracy, and together they form a robust GNC sensing architecture. Let's shift to the actuation side of the GNC subsystem. How do orbiters actually change their orientation in space? It all comes down to exploiting the environment, and this slide shows the key types of actuators we use, based on what physics we can leverage. Let's start with momentum control systems, like reaction wheels. The images in the top right show a spinning wheel inside a spacecraft, or a reaction wheel. The spacecraft body rotates in the opposite direction that the wheel spins up in, and this is a direct application of the conservation of angular momentum law. Reaction wheels provide fine, continuous control with high precision and can operate on all 3 axes if you have reaction wheels pointed in all 3 axes. But over time, they build up unwanted momentum from external disturbances, so we need a way to dump that extra angular momentum. That's where magnetorquers come in, shown on the bottom right. These are coils or rods that create magnetic dipoles, and those magnets interact with Earth's magnetic field, producing torque. They're lightweight, energy efficient, and great for momentum offloading. But they're also environment dependent. They only work near Earth or other planets with magnetic fields, and the torque is limited to 2 axes at a time due to the cross-product relationship. In more demanding missions, we may use reaction control thrusters, like those in the image of this Apollo service module. These little thrusters apply forces off-center from the spacecraft's center of mass to generate torque. They're powerful and responsive, but they use repellent, so they're limited by fuel, which makes them less ideal for long-duration attitude control. Then there's the gravity boom, seen on the left. This is a passive method that uses gravity gradient as a torque. By extending a long boom with a small mass at the end, which is up there, the spacecraft naturally aligns itself with the local gravity field, like a pendulum. This only works in low orbits and only provides control in one axis, but is power-free and extremely reliable. Your actuation system will likely be a combination of these tailored to your mission environment and lifetime. Think of these actuators as a toolkit. Your choice depends on what physics are available and how much control authority you need. Let's see an actual implementation of a GNC subsystem for an orbiter. In this case, the Dark Ages Radio Explorer, or DARE for short. DARE is a lunar orbiter designed for radio astronomy, which requires extremely stable and quiet pointing. Its GNC system uses a 3-axis stellar inertial design, so star trackers provide precise orientation, while gyros, which are in the MENS IMU, propagate attitude during science to avoid electromagnetic noise. Reaction wheels handle fine control, and RCS thrusters manage delta V and momentum dumping. The system is built from flight-proven hardware used in missions like Kepler and Deep Impact giving DARE a low-risk, high-margin solution for its strict pointing requirements. To understand what sensors and actuators are needed for a lander's guidance, navigation, and control, let's walk through Mars 2020's entry, descent, and landing subsystem as a case study. The environment on the top left tells us what physics are at play. So remember, for Mars, that is gravity, thin atmosphere, and varied terrain, but no magnetic field to leverage. That means that every phase of the concept of operations, from exo-atmospheric navigation to hypersonic entry to parachute descent and powered landing, must be handled by carefully chosen hardware that only leverages the physics available. Now we'll step through the sensors and actuators seen up here that are needed to guide the vehicle through this complex autonomous sequence. For landers and entry probes, sensing is all about surviving the descent and landing safely on often unpredictable terrain and doing that quickly and autonomously. So using Mars 2020 as the architecture for case study, it's one of the most advanced examples to date. At the core is, you can guess, the IMU, which measures acceleration and angular velocity continuously throughout descent. It's used for propagating the vehicle state when other sensors are unavailable, like in atmospheric entry. Then we have this landing radar, shown here with its multi-beam antenna. This gives us real-time measurements of altitude and vertical velocity relative to the surface, a key input for triggering power descent and sky crane maneuvers, which happen at different altitudes. The lander vision camera, shown over here, provides high-resolution images of the surface during descent. These are matched against an onboard map to estimate horizontal position along the Martian surface. That is terrain relative navigation in action. Together, these sensors allow the lander to estimate its full 6 degrees of freedom state and execute autonomous hazard avoidance and land safely. Additional sensors used in past lander or probe missions include LiDAR, as in Chang'e, contact switches on asteroid probes like Hayabusa, and Doppler velocity sensors on Viking and Huygens, and laser rangefinders on the Philae lander. The exact combination of the aforementioned sensors depends on the descent phase, the target body, and the mission objectives. For landers and probes, actuation during entry, descent, and landing needs to be tailored to that target body's gravity, atmosphere, and surface. Using Mars 2020 again as the central example, the mission begins with an aerodynamic control and parachutes, which provide passive deceleration in Mars's thin atmosphere. This phase takes advantage of fluid flow physics, something that's only possible on bodies like Mars, Venus, or Titan. Then, as we get closer to the surface, we transition to power descent using engines, like the retro rockets on the descent stage. These engines enable precise control during final landing. Thrusters offer attitude control or small trajectory corrections. They're often used during descent or for momentum management, as seen in both the Mars and Apollo missions. Now let's focus on landing gear. While landing gear wasn't on the Mars EDL architecture, we're using the Europa lander as a more modern example. It's just a concept. Here you can see that there are these legs, and these legs include shock absorbers, crushable honeycomb structures, or articulated dampers. They absorb the impact of touchdown and provide stability on uneven or unknown terrain, a critical component for any surface mission. Other actuators worth noting include entry balance masses, which are in Mars 2020's EDL, and that helps with stabilization and trajectory control. And then there are also deployable systems we've seen in previous lectures, like airbags or booms. Something I won't talk too much about are all the algorithms that are running in the background. But here is a flow diagram which shows how Mars 2020's GNC systems integrate sensors, estimators, and control algorithms to execute a fully autonomous landing. At the bottom left, we start with raw measurements from the IMU radar and vision system, feeding into a navigation filter that estimates position, velocity, and attitude throughout descent. State estimates from the navigation filter then drive guidance logic, which includes entry guidance and some trajectory profiling. Finally, actuator commands are generated accordingly, whether that's for thrusters, descent engines, or attitude control. So there are commanders here and here. As we get closer to the surface, terrain relative navigation kicks in from an EDL mode commander, searching for and selecting for safe landing zones in real time. This is a closed-loop architecture that allows the lander to sense, decide, and act at update rates as high as 200 Hz to safely land on the Martian surface. To navigate autonomously on planetary surfaces like the Moon or Mars, rovers must continuously sense and estimate where they are, how they're moving, and where it's safe to go. On the top left, again, those are reminders as to which references you can use. In these planetary surface environments, we have gravity and terrain for reference, but no magnetic field. And star visibility may be limited depending on the time of day or sky conditions. Let's walk through the suite of sensing methods used to achieve these three functions: relative localization, global localization, and hazard avoidance. We'll start with relative localization. That's estimating your motion over time without referencing a global map. On the top left, we have inertial navigation in wheel odometry. This uses the IMU with gyroscopes and accelerometers alongside wheel encoders to integrate small movements into an estimated path. It's lightweight and self-contained, but it drifts over time. To correct for that drift, we can use visual odometry, which compares successive camera images to track the motion of features in the environment. This gives very accurate short-term movement estimates and helps the rover measure slip when traversing sandy terrain. Now, let's move into global localization, which ties the rover's position or orientation to a planetary reference frame. Stellar positioning, shown in the left, uses a star tracker to image the night sky and determine the rover's orientation based on known star fields. This works well for missions with clear skies and no atmospheric interference. For position, we can use surface navigation based on orbital imagery. Here, local camera images are matched to preloaded orbital maps, like satellite imagery of the surface, to estimate where the rover is. A similar approach uses orbital elevation maps, or DEMs, where local 3D terrain is aligned with global elevation data to triangulate the rover's location. Another powerful technique is crater-based navigation. Craters are persistent features that can be detected locally and matched to orbital maps. This method has been flight tested and is robust in low-feature terrain. In some cases, like with skyline-based navigation, the rover captures the horizon outline and compares it with a predicted silhouette based on its surroundings. It's like a visual compass using the shape of the surrounding terrain. For hazard detection and path planning, rovers rely on stereo cameras or LiDAR to generate 3D terrain maps. These maps are classified into safe, marginal, and unsafe zones, and planners use that information to find a traversable path. Finally, tying everything together is SLAM, or simultaneous localization and mapping. This allows a rover to build a map and localize within it at the same time, particularly useful when no prior map exists. SLAM combines odometry, camera data, and landmark tracking to both navigate and explore new environments. Of these many methods, each method has trade-offs. Missions often use multiple techniques in parallel. For instance, Perseverance combines wheel odometry, visual odometry, terrain mapping, and orbital map registration to ensure robust localization under all conditions. Now let's talk about the actuators on a rover that enable control and locomotion. We'll start with the diagram in the center, which breaks down the motor counts on the Curiosity rover. Of the 31 motors on board, 10 are dedicated to mobility, 6 for wheel drive and 4 for wheel steering, enabling both skid steering and tight turn maneuvers. These actuators are what allow the rover to traverse uneven terrain and execute planned paths from the GNC system. On the bottom left, we see images of those brushless DC motors made by Maxon, the same company that built motors for both Perseverance and Ingenuity. These motors, such as the EC32 and EC20 flat series, are compact, lightweight, and optimized for vacuum and radiation environments. making them ideal for high reliability GNC applications. While the motors provide torque, it's worth noting that the wheels themselves are carefully designed for traction. To the right, we compare Curiosity and Perseverance's wheels. The zigzag browsers, those raised ridges, help grip soft soil, distribute load, and resist wheel slip. These aren't actuators themselves, but they directly influence GNC performance by improving traction and terrain handling. Lastly, I'll just mention the robotic sampling arm. And it's not used for locomotion, but it does include actuators that interact with the terrain. And its configuration must be tracked by the GNC system to maintain balance and avoid tip over during sampling operations. Let's now talk about aerial vehicles and how they navigate with the various sensors constrained by the references set by their environment. In this slide, we'll use Ingenuity, the Mars helicopter, as a case study. As a reminder, Ingenuity operates in an environment where we can use gravity, stars, and Martian surface features, but there are weak magnetic fields that we can't use for navigation. That limits the external references. Through those limited external references, we've made the most that we can with these sensors on board. Due to sole daytime operations, the helicopter ended up not using a star tracker because it's daytime, although that reference was theoretically available. On the top right, we highlight Ingenuity's operational capabilities. It takes off, it hovers, it can translate in flight, capture images, and land, all autonomously. These actions require precise attitude and position estimation in real time, which is especially challenging in Mars's thin atmosphere. To the right, we can see the kind of data Ingenuity produces. Downward-facing images from its nav cam showing the shadow of the helicopter against the Martian surface. These images are used for science, but they're also used for optical flow tracking and visual odometry during flight. In the center here, we look at the CAD of Ingenuity's flight body, which is this box over here. On board, there are a bunch of sensors, two of which are IMUs, one down here and one up here, which provide angular rate data at a high frequency for attitude propagation. Ingenuity also has a laser altimeter used to estimate height above the ground during descent and hovering. An inclinometer provides course gravity direction before takeoff, helpful for initializing attitude. For vision-based navigation, Ingenuity uses a low-resolution black and white navcam, which supports fast frame rates for tracking features. This is mounted downwards and works together with IMU data for visual inertial odometry. And finally, there also is a return-to-Earth camera, which is mounted forward-facing and used to capture high-resolution images for understanding the terrain and documenting the mission, though it doesn't contribute to navigation in real time directly. Each of these sensors is tightly integrated with Ingenuity's GNC software to provide real-time estimates of attitude, velocity, altitude, and position, making flight on Mars possible despite the lack of GPS or strong atmospheric cues. Let's wrap up the various architectures and technologies with how aerial vehicles, like Ingenuity, actually achieve motion using onboard actuators. Again, recall the flight concept of operations. We have to take off, we have to hover, navigate, image, and land, all autonomously. These phases are executed using just a few key actuators. At the heart of Ingenuity's design are two coaxial brushless DC motors, shown here from Maxon. These power the upper and lower rotors, which you can see here, upper, lower. These rotors spin in opposite directions to generate lift and cancel torque, enabling stable hover and yaw control. To steer and maneuver laterally, forward, back, and side to side, Ingenuity uses 4 servo motors connected to a swash plate assembly, shown in the cutaway to the right. There are 2 tilt motors per rotor, giving you 4 total motors. So while there are motors for the rotors, there are also these servo motors, 2 each per rotor, which you can see down here. They cyclically tilt the blades to modulate thrust vectoring. That's how the helicopter achieves pitch and roll control for translational flight. The entire actuation strategy is lightweight and highly efficient, critical for flight in the thin Martian atmosphere. And unlike a drone on Earth, there's no GPS or live pilot, so every actuation command is driven by some onboard state estimation and GNC logic in real time. While the system is mechanically simple, just 2 main rotor motors and 4 tilt servos, it still enabled precise, stable, and autonomous aerial mobility across an extraterrestrial surface. Given all of these technologies to choose from and then blending them together, how do you ultimately know that that combination of sensors or actuators are going to get you the performance that you want? You need to verify them. To verify your GNC subsystem, you need to test in environments that replicate the sensing references and physics your system will face in the real world. That can be done through simulation or through different analog tests. Let's start with simulation. Tools like GMAT can model orbital dynamics, spacecraft attitude, and control maneuvers. They're useful for early design validation, running Monte Carlo analyses, and visualizing trajectories and pointing. For surface systems, physics-based simulation, like this custom soil interaction model shown here, allow us to test wheel-soil dynamics and rover mobility. Beyond pure software, you can step up to software-in-the-loop and processor-in-the-loop tests, where you validate your GNC code in a simulated environment or on the real flight processor. On the other side, analog testing means testing with hardware in physical environments. On the top left, you see a prototype of Ingenuity inside a vacuum chamber to replicate the thin atmosphere and low gravity of Mars. In the middle is the Hawaii Spaceflight Lab's ADCS testbed, where we spoof sensor inputs through a Helmholtz cage, a sun simulator, and a GPS simulator while testing spacecraft motion on an air-bearing platform in the middle. This setup supports hardware-in-the-loop testing, combining simulated environments with real flight hardware. To verify surface systems, we can do field testing, like in JPL's Mars Yard, where a mass-reduced rover navigates real obstacles in terrain resembling the Martian surface. This lets us evaluate both mobility and GNC autonomy in a realistic operational scenario. Together, simulation, analog testing, and hybrid methods like hardware-in-the-loop and field testing help ensure your GNC system will work in the environments it was designed for. I hope you are now able to define the function of a GNC subsystem, identify typical requirements and design constraints, and understand how different technologies are applied for guidance, navigation, and control across satellites, landers, rovers, and aerial vehicles. Thanks for allowing me to share my favorite topic with you. See you next time.